Dear friends, welcome you all for today's class. Today we are going to discuss to derive very important relationship between area, velocity, and specific volume. Area, velocity, specific volume, and pressure during flow through nozzle. When steam flows through nozzle, what are relation between pressure, velocity, and even Mach number you will see that in that equation Mach number will also appear. So you will know that mostly in aeroplanes, jet aeroplanes, and spaceship rockets, and there are so many applications of convergent divergent nozzle. But here specifically we are discussing for the steam turbines, which are major power developer in thermal power plant, because we know that in thermal power plant working fluid is water, and water is converted into steam from boiler. Steam is supplied from boiler to the turbine at very high pressure and high temperature. So in a turbine there are two or three stages in which there are fixed blades and moving blades. So fixed blades, these are act like nozzles. So nozzle function of nozzle is to convert pressure energy into kinetic energy. Means high velocity steam will come out from the nozzles exit. Mainly convergent divergent nozzles are used in steam turbines. So here, but these nozzles are also used in jet engines. Jet engines, when exhaust come out with very high velocity from jet engine, that is a function of nozzles which convert pressure and temperature. Pressure and enthalpy means total heat energy, in which pressure and temperature both will include, convert into kinetic energy, so that because mostly turbines act like reaction turbine, reactions and impulse both are combined together. So it is a mix of the reaction and impulse turbines. In impulse turbines, very high velocity steam is required. So these are nozzles, convergent divergent nozzles, which convert pressure energy into kinetic energy. So here we are going to see what is the relation between velocity, area, and pressure in these while steam flowing through nozzle. So let us draw a diagram first. So see, this is a nozzle. This is a convergent divergent nozzle. So this is a convergent divergent nozzle, and we see take two section here, section 1, and 2. So this is a exit condition. Let us see here the pressure is here, velocity is C, initial velocity is C, and specific volume is V, and area is A. We are taking here three parameters. C stand for the velocity, speed, V small v stand for the specific volume, A stand for the area at this cross section, because you know that this is a three-dimensional nozzle, and so we have taken divergent part, so area is continuous, because here is velocity suppose changes from C to del C, because we have taken del x thickness. So C will change C to C, and V change to V plus del V, and A change to A plus del A. And we have considered that this is a isentropic flow, reversible adiabatic flow. There is no any frictional losses, and the flow is a full flow. Means nozzle is flowing, working fluid is flowing through nozzle full flow. Means there is no empty partial flow. There is a full flow. So we will apply continuity equation at all three sections. Inlet, and this will be throat of the nozzle, and this is the exit of nozzle. At any section of the nozzle during a flow, we can see continuity equation, means the mass is flowing at constant. There is no any accumulation of any parameter which are changing with respect to time at any point. So it is a steady and continuous flow. So M1 will equal to M2. So A C upon small v equal to A plus del A, and C plus del C upon V plus del V. Simply we have taken at 2, we have taken at cross section 1 and 2 and applied continuity equation. So now simplifying this equation, AC V multiplying this one, AC del V equal to A plus del A and C plus del C into V. So multiplying this also we multiply. So ACV plus AC del V equal to first ACV plus A del CV plus del ACV plus del A del C, multiplying all parameters. So we can see that now some will be replaced. So here let us see, ACV will be replaced by ACV, and one thing you can see, there are two small product here. You can see del A and del C are very small. Here del A and product of del C, we are already very small terms, so we can neglect, because this is a double product of two small quantities del A and del C. So this can be neglected. You can neglect without having any significant impact on the result. So now remaining parameter will be, you see, ACV, AC del V, AC del V equal to CV del A plus AV del C. So now dividing whole equation with dividing whole equation. This equation we can divide by dividing whole equation ACV by ACV. So we get here del V by del V, del V by V equal to del A upon A plus del C upon C. So this is you see, you get equation del A by A equal to del V by V minus del C by C. This is equation. So now we can say, suppose these quantities are approaching to 0. Del A tends to 0 and del V tends to 0 and del C tends to 0. So this equation can be replaced like a dA by A. When quantities become very small, dA by A equal to dV by V minus dC by C. So this is the final equation number 2, you can say. And we know one thing, that this flow is isentropic. So, and for the steam, we can write this equation is followed in this flow equal to constant PV to power n equal to, already we have derived all these equations. So PV to power n equal to constant, taking log of this equation. So we get log P plus n into log V equal to 0, and taking a differential of this equation, partial differential of this equation, we get dP by P plus n dV by V equal to 0. So you can write dP by P equal to minus n dV by V, or we can say dV by V equal to minus 1 upon n dP by. So this we will use in finding out these values. So now you can see, here we erase this one. Right here dV by V equal to minus 1 upon P dP by T. Now another equation that we are going to use, that is momentum equation. Already we have discussed momentum equation, that was C2 square minus C1 square by 2 equal to integration P2 to P1 and VdP. This equation we have already discussed, that this is the momentum equation during flow. So if we take differentiation of this equation, differentiate this equation, and considering C1 tends to 0 and C2 equal, because when C1 becomes 0, then C2 we can take C, and differentiating this equation we get CdC equal to minus VD. This equation, if you again integrate for definite integral from C1 to C2 and from P1 to P2, you get again this equation. Try this, integrate this equation for definite integral of C1 to C2 and P1 to P2, you get same equation. So reverse is series of this momentum equation, CdC equal to minus VdP and DC equal to minus V by C dP. So DC by C equal to minus V dP by C square. Putting all these two values, one value we have taken dV by V, another value we have taken DC by C in this equation, because we have to put value dV by V and DC by C from this equation. So now you get equation dA by A equal to dV by V, we have taken minus 1 upon P dP by P, and dC by C equal to minus VdP. So it will become VdP by C square. Now taking common dP by P, that was something missing, I think 1 upon N. dP by V minus 1 upon N, that was minus 1 upon N. I am missing here. This one is a minus 1 upon N. So correct it, minus 1 upon N. So it is a minus 1 upon N here, minus 1 upon N. This is 1 upon N. Here you see that was a minus 1 upon, by mistake I have put here minus 1 upon P. So now taking common here, we will take common 1 upon N, 1 upon N dP by P common. Take outside, so we get NPV. Here we get NPV upon C square and minus 1. So dA by A equal to minus 1 upon N dP by P. In bracket you see 1 upon. So next we will take this equation. We have derived dA by A equal to 1 upon N dP by P in bracket NPV upon C square minus 1. See here what is NPV, and we know that velocity of sound in any medium, that is equal to root NPV. This is the velocity of sound. So NPV equal to A square. So putting value here, so 1 upon N dP by P equal to A square upon C square minus 1. And we know that Mach number is Mach number is equal to C upon A. Velocity of steam upon speed of sound in steam. C upon A velocity of steam upon speed of sound in steam, that is A, that is NPV. We have taken under root NPV equal to A square equal to NPV. So this is this one equal to, further simplifying, dP by P 1 upon m square minus 1. So dA by A equal to 1 upon n dP by P, further simplifying 1 minus m square upon m square. So this one is a most important relationship of the nozzle flow, having relationship between area, pressure and velocity. M is nothing but velocity means C, steam, because C is coming, A remains constant, so C is important. Means velocity of steam that is coming, that includes in Mach number M, and dP by A is pressure and dA by A is area. So let us now discuss nature of this equation. Let us see what are conditions of flow through nozzle. Case 1, we take case 1. There is a case 1 is a accelerated flow. What will happen? Because we know that acceleration will take place when pressure is decreasing. Because pressure energy converting to kinetic energy. So in accelerated flow, pressure is decreasing, means dP by P. In this equation, dP by P negative. Because pressure is decreasing, that is accelerated flow. So now three conditions are possible. Condition 1, C less than A. Velocity of steam is less than velocity of sound. So here you can see in this equation, dA by A equal to 1 upon N dP by P 1 minus m square upon m square. When C is less than A, so m is less than A. So this quantity in bracket is positive. 1 minus less than 1 square upon m square this is always positive, and this is always negative, because already we have taken for accelerated flow dP by P is negative. So to balance this equation, dA by A by must be negative. This means that dA by A turns negative. This means that, and dA by dA is negative only for the convergent nozzle. This is only possible for the convergent nozzle. Case 1 is for the convergent nozzle. When accelerated flow C is less than A, means velocity of steam is less than velocity of sound, so it is for convergent nozzle. And second case, C equal to A means M equal to 1. Now this will become 0. So when this becomes 0, so dA by A becomes 0. So means dA equal to 0 means A remains constant. There is no variation in cross section. So this is for the thought. This is for the thought. This is for the thought. This is for the thought, because in thought region area remains constant. So for the C equal to, it means a thought velocity will become equal to velocity of sound, means sonic velocity. Steam will pass from the thought at the sonic velocity. Third case third, T greater than A means velocity of steam is greater than velocity of sound. So M become greater than 1, and in this equation, when M become greater than 1, this whole value in bracket become negative, and dP by P is already negative, so negative become positive. So now dA by A become positive. So dA by A become positive. So this means that now this is a case of the divergent nozzle. This is a case of the divergent nozzle. The nozzle will become, shape of the nozzle will become in this region, that is a divergent. If velocity become greater than A, so it is a region of the divergent. This is a divergent nozzle. So all three cases are possible for the accelerated flow. Already we have covered. Now we will take case of the decelerated flow, means when pressure is increasing and velocity is decreasing. This is a decelerated flow, means case second. We will take decelerated flow. So let us see what happened for the decelerated flow. In that case second. First case we have taken accelerated flow, and now this is a decelerated flow. Decelerated flow. So for decelerated flow, we know that dP by P is positive. dP by P is positive. So case 1, first case we take C less than A. So M less than A. When C less than A, M less than 1. So positive, this value in bracket is positive, and dB by P already positive. So dA by A is positive. So here dA by A is positive for case 1. So here nozzle is diffuser, that is a divergent. Nozzle will become divergent type, that is this one. This one is a diffuser. And case second, when C equal to A, M become equal to 1. So bracket, this value will become 0. So dA by A become 0. So again this one become a thought. So this is the case when accelerated flow or decelerated flow both are same. Whether it is a accelerated flow or decelerated flow, when C equal to A, it is the region of the thought where C equal to A, means in accelerated flow or decelerated flow, condition of the conduit will become a thought. Now here we will take a third case. Case third, C greater than A. In this case, M become greater than, Mach number become greater than 1. So here this value in bracket become negative. This we have taken positive, and so whole value in right side become negative. To balance this dA by A, so it become negative. So in that case, it is a divergent, it is a convergent diffuser. Diffuser will become a convergent because it is a diffuser which provides decelerator. So in that case, when velocity is already C is greater than, means velocity of steam is greater than velocity of sound. So for deceleration, we have to use convergent diffuser. Otherwise, already velocity, to reduce the velocity, we have to use convergent diffuser. So all these two cases are very, very important. This is one of the most important discussion of the nozzle, in which you will find always very tricky question, objective type question in GATE examination, in Indian Legal Service examination, in many Bhabha Atomic Research Center examinations, and so many public sector. You will always get two or three questions from this topic. So this is very very important. I think this decision make your concept crystal clear. I think it is any doubt if you have, please ask me to further explain, and we will solve some questions. So this is, I think, good for you. If you like it, please subscribe and also share to your friends. Thank you very much for sharing your time in watching this video. Thank you very much and have a nice day.